So in the last lecture, we started discussing about community structure, and we have seen, we basically, I tried to motivate you why it's an important problem and why it's a non-trivial problem. Okay, so here we will discuss different types of community structures. Okay, there are generally 3 types of community structures, but sometimes there are one more type. So there are essentially 4 types. So the first type is disjoint communities. It is also called as flat communities. Okay, what's a disjoint community structure? In a disjoint community structure, a node can only belong to a single community. A node can belong to at most one community, at most and at least one community. So exactly one community a node can belong to. Okay, let's look at this example. Here you see that each community, this circles, right? Different circles. These circles indicate different communities. So there are 4 communities, and you see that a node can belong to only one community. Okay. So the next one is overlapping community. What is overlapping community? In overlapping community, a node can belong to more than one community. Okay, and this is more natural. If you think of social networks, right, this is more natural. You can be a part of, say, Sachin Tendulkar fan club, you can be a part of Narendra Modi fan club, you can be a part of Bollywood movies, and so on and so forth, right? A node can, at the same time, a node can belong to multiple communities. So if you look at here, say this node, okay, this node is a part of the black community as well as the green community. Okay, so say this node, right, this node is a part of the red community as well as the blue community, and so on and so forth. So disjoint community detection is of course difficult, but overlapping community detection is even difficult, more difficult. Why? The reason is that if you think of an exhaustive way to detect communities, right, say you have certain function f, okay, a certain function f, and you have a network where you have different nodes, okay, and let's assume that the number of communities. Okay, let's assume that that there cannot be more than 2 communities. Okay, so what are the possible ways to group nodes into 2 communities? There are different ways. For example, one grouping would be this, okay, another grouping would be this, and so on. There are many ways, right, of grouping nodes into 2 communities. What about overlapping community? So this is disjoint community. When it comes to overlapping community, the number of possible options will increase exponentially. Okay, so therefore overlapping community detection is even more difficult than a disjoint community detection. The third one is called hierarchical community. In a hierarchical community, as the name suggests, so our nodes are grouped into different hierarchies. For example, in a student interaction network, right, say for example the low level groups, right, you can think of low level groups as say these are students. Okay, the first level grouping can be done based on based on year. So first year, second year, third year, fourth year. So this is first year student, second year student, third year student, and so on. Okay, the next level grouping can be this first year, second year, third year computer science, right? You have another first year, second year, third year ECE. Okay, again another level of grouping can be the CS, ECE, IT, right? This will form engineering, right? Then you have other science subjects, physics, chemistry, that would form science, right? Similarly, you have arts, you have commerce, right? And then the science, arts, commerce can again further be grouped into an institute. Within an institute, you have science, arts, commerce, and then within science you have a different branch, within engineering different branch, and so on, right? Then you can group them based on institutes, right, and so on and so forth. So again, hierarchical structure is quite obvious, quite frequent in our day-to-day world. If you think of even biological network, right, we see cells, proteins, cells, tissues, and so on and so forth, right? So So these are the main community structure types, right? But sometimes people also say that there is another structure, another type of community is called local community. What is a local community? Local community is a community with respect to a particular node. So let's say if somebody asked me, tell me the local community of vertex V, right? So the output would be a community where the node V belongs to, right? So what do you mean by returning a community? Basically I need to return other nodes which are also part of the community. So I am only interested in that community or those nodes which are part of the same community where the node V belongs to. Okay, right? Say these are the nodes which are also part of the same community where V belongs to. So if the query is to return the community, the local community of node V, I will only return, right, the nodes which are part of the same community. This is called local community. So local community detection is important, with respect to certain applications. For example, in a social network, it's a gigantic network, right? And it's very difficult to detect communities at every day, because network grows over time, and it becomes exponentially larger and larger over time. So nobody runs overlapping commutation algorithms or non-overlapping commutation algorithms from the scratch. What people do is generally, when people basically query for a particular vertex, for a particular node, and the output should be the community for that particular node. So this local community detection is very important in the context of, say, recommendation system, in the context of other types of. So you say you want to understand, you want to profile a particular user, you want to understand what are the other users who this particular node V interact with most of the times, right? So we are not interested in other nodes, we are only interested in a part of the node, a part of the network which the node interacts with quite frequently. Okay, so there the local community detection algorithm would be useful. So if you look at the algorithms, right, the algorithms for community detection, so this is the brief taxonomy. You see here, you broadly classify into disjoint community, overlapping community, local community. We generally do not talk about hierarchical community, because hierarchical community structure can automatically be detected during the process of, say, disjoint community detection. We will discuss later that while detecting disjoint communities, we also unfold the underlying hierarchy. Okay, so we do not need to explicitly detect hierarchical communities. Okay, so disjoint community, overlapping community, and local community. So within disjoint community, we will see methods like some node-based, node-centric measures. We will see a metric called modularity, right? There is another set of algorithms which are based on information theory, entropy, etc. So this part I will not cover, but if you are interested, you can go back and check. We will also discuss another metric called permanence, which turned out to be highly effective, and we will discuss some dynamic algorithm. For overlapping communities, we will discuss click percolation, right, link partition, big clam, and some some variations of permanence called gen-perm. Okay, and for local communities, we will also discuss local expansion and some other inference model. Okay, so this is more or less the topics that we are going to cover in this chapter. Okay, so let's start with a simple way of detecting communities. Let's look at some of the node-centric metrics. Okay, so generally we classify these strategies, the node-centric detection, into three groups. One is called complete mutuality, right? The second one is something called reachability of members, and the third one is node degree. Okay, we'll discuss all these things one by one. So let's start with the complete mutuality, and this is the trivial definition of a community. Okay, so according to this one, a community is basically a clique. Okay, what is a clique? A clique is a completely connected graph where all the nodes are connected to each other. Okay. So if you think of this part, this is a clique because all the nodes are connected to each other. This is also a clique, all the nodes are connected to each other. So it's a very stricter definition of a community. Okay. So essentially community detection is nothing but finding cliques in this case. Okay. And it turned out, if you see the literature, it turned out that finding cliques from a network is an NP-complete problem. Okay. So therefore, I mean, we generally do not detect cliques. We try to reduce the restriction of connections of all pairs of nodes. So therefore, we relax the restrictions in some ways, and then we come up with we can think of different definitions. For example, this one. So this is called K-clique. So we are not interested to detect cliques. We are interested to detect something called K-cliques. What is the K-clique? A K-clique is the maximal subset of vertices. So please read this definition carefully. Okay. A K-clique is the maximal subset of vertices of the network such that for any two nodes belonging to this subset, the shortest distance between them is less than equals to k. There are two conditions here. The first condition is it should be a maximal subset. The second condition is between any pair of nodes in the subset, the distance, the shortest path distance should be less than equals to k or less than k. Okay. So let's try to understand this slowly. What do I mean by maximal subset? I hope you know the difference between something called maximum and something called maximal. Okay, what's the definition? What's the difference? Let's say you have a set. Okay, you have a set. You have some number. You have some numbers or some entities, right? Okay, and you have certain function. This function is defined on a set of elements in this set. Okay, and you want to maximize this function. Okay, so you see that when I do not know what's the function. Let's assume that's a function, and this function takes into account different elements from the set, and then it returns some value. Okay. And our task is to get the maximum value of this function. So the task is to identify those elements which you input to this function will return the maximum value. Okay. And let's say when I add a b, right, I get the maximum value. Let's say the maximum value is 0.8. Okay. When I add a b, when I add c here also, I also get the same value 0.8. Okay. So this AB, this subset AB is not maximal. It is not maximal. Why? Because if you add another number, another element C, it still gives the maximum value. Okay. Let's say ABC now gives the maximum value, right? And if you encounter a situation that after ABC, whatever element you add, the value will decrease. Whatever element you add here to the function, the value will decrease. Then you stop, right? So your a set that you return is ABC. So AB is not maximal, but ABC is maximal. This is maximal. Okay. So now let's see. Let's think of another solution. Say you added E, F, right? You got 0.8. Okay. You again add D, you still got 0.8. You add C, you still got 0.8, right? But then you start adding the other elements, the value will decrease. Okay. So you freeze this. So your another maximal element is E, F, D, C. Okay. So this is one maximal, this is another maximal, right? These are maximal because if you add another element, it will not give you the maximum value. It will not give you the the best value that you can obtain from the function. These are maximal. Now what's the maximum value? What's the maximum set? The maximum set is this one. Why? Because in this particular set you have 1, 2, 3, 4, 4 elements, but in this set you have only 3 elements. So in terms of the size, this is the maximum. So there can be multiple maximals, but there should be always, of course, one or more than one maximum, but it should be unique, right? So in this case, the maximum set of the set size would be 4. Say, let's say there is another set, right? There is another subset, say A, B, D, E, G, right? This also produces the same output 0.9. In that case, this is maximum. Why? Because the size is 5. But let's say there is another set, right? A, B, C, say A, B, D, F. This also produces 0.8. So these and these will be maximum, because there is no set, there is no subset of size 5 which satisfies the condition. Okay? So this is the difference between maximum and maximal. Okay, now let's again look at this definition. It basically says that I want to detect a maximal subset of vertices, okay, such that for every pair of nodes in that subset, the shortest path distance should be less than equals to k. Okay? Let's think of a clique. So this is a clique, right? All the nodes are connected. What's the k value of this clique? If it is a k clique, what's the k value of the clique? Shortest path distance is 1 between any pairs of node. Between any pair of nodes, the shortest path distance is 1 always. So this is one clique, right? Now let's look at this figure, right? So you have 1, 2, forget about this square, okay, this boundary, just focus on the network. So you have 1, 2, 3, 4, 5, 6, 7, there are 7 nodes, right? And let us group these 5 nodes. So now tell me whether this is if this is a k clique, if this is a k clique, then what's the value of k? So if you look at the distance, right, if you look at the pairs, every pair, you take any pair, okay, let's say this one, the distance is always 2 or less than 2. If you take 1 and 2, distance 1, maximum distance is 2, shortest path, right? You may ask, how is it so? Because if you look at 3 and 5, the distance is 1, 2 and 3. No, the distance is 2 because there is no node 4, right? Through 4, it has distance 2. But although 4 is not a part of this group, doesn't matter. It basically says that let's take a subset, right? It does not say that when I calculate the shortest path, I only look at those edges which are present within the group. Look, in the definition it is not mentioned. So it is not mandatory that when I calculate the shortest path, I only look at those edges which are part of this group. Okay, I can take these edges which are not part of the group. Okay, so therefore this is a 2 clique. Okay, what's the problem here? You may have already identified the problem. The problem here is when we calculate shortest path, right, we may consider nodes and edges which are not part of the this particular group. That is wrong, right? So there should be a restriction on the edges or nodes which we are considering while grouping nodes, right? So in order to address this problem, the second definition is proposed. It's called K-clan. The names are quite ambiguous, so please remember the differences. So we have clique, a relaxed version of clique called K-clique, right? And then we have K-clan. What is this K-clan? So it's a stricter version of K-clique. Okay, The definition is more or less same. Only difference is that when we calculate the shortest path, we only take into account those edges which are part of this group. So the definition says that it is basically a maximal subset of nodes, right, within which if you create the induced subgraph based on the nodes, based on only the nodes which are part of the group, you create the induced subgraph. So when I say that induced subgraph, I am discarding those edges which are not part of this group, right. So for example, in this case I am discarding this edge and this edge. So I only take this structure 2, 6, 3, 5 and 4. Okay. So it's a maximal subset of nodes such that if we take the induced subgraph, right, of these nodes, right, the distance between any pair of nodes should be less than equals to k. Right. Now think of this case, right. If you take any pair of node from this particular group, in this particular group, you see that the distance is always 2. So it's a 2 clan. But this is not a 2 clan, right, and the reason is simple because when I take the induced subgraph, right, I will not consider this edge and this node, right. If I do not consider this one, then we will have only this part, and between 3 and 5 the distance is 3. So this would be 3 clan, because the distance between any pair of nodes is always less than equals to 3 in this case. Okay. So a stricter definition of this one is k clan. So k clique, then k clan. Okay. So what about let's take another case. Let's take another counter example. Let's see. Let's take let's take this one. 1, 2, 3, right, 4, 5, 6, right. Let's take all of them together. Is this a 2 clique? Is this a 2 clan? This is not a 2 clan, right, because the distance from 1 to 4 is 3, right. What about this one? What about this grouping? Say 2, 3 and 2, 3, 4, 5. Is this a 2 clan? If you look at the distance, or say let's say this is wrong example. Let's think of this one. Say 2, 3, 4. Is this a 2 clan? If you take any pair of node, the distance is less than equals to 2. You may say this is 2 clan. This is not a 2 clan. Why? Because this is not the maximal set. This is not the maximal set. If you add 5 and 6, the set will increase, but it still remains a 2 clan. It still remains a 2 clan. Remember this term. So maximality should be preserved and the distance constraint should be preserved. Okay. So now let's look at another definition called K club. So these definitions are little ambiguous but interesting. What is K club? So K club is same as K clan, but if we remove the maximality condition, then it's basically K club. So K clan minus the maximality condition equals to K club. Basically what I mean to say is that a K club is a subset of nodes whose induced subgraphs, if we take the induced subgraph of those nodes, the distance between any pair of nodes should be less than equals to K. So in that case, this is a K club, right? This is also a K club. This is also a K club, but these are not K clan. Now think about it. So K clan is the strictest definition of the most rigid definition of a community, right? If you just ignore clique, so K clan is the rigid definition. Then a relaxed definition is K club, where we relax in terms of maximality, and another relaxed definition is K clique, where we relax in terms of the induced subgraph property. Okay. So there is another notion called K-plex. Okay, what is K-plex? K-plex is a subset of vertices S in a network such that if every vertex of the induced subgraph, so induced subgraph constant is there, right. So I take the subset S, I draw the induced subgraph, right, and then I look at the degree of every node. The degree should be at least mod S minus K. Mod S is the size of the set that we choose, and K is the K-plex K. Think about it. You choose a node, you choose a set of nodes S, then you create the induced subgraph GS, right. Then you see then you basically measure the size of the set mod S. Then you look at the degree of individual nodes, right, and based on that you decide whether it's a K-plex or not. Let's take an example. So say 3, 4, 5, 6. Okay. So I take the induced subgraph. So the induced subgraph would be this one, 3, 4, 5, 6. Okay. And then what's the size of S? Size is 4. And what's the minimum degree? Because at least, right, what's the minimum degree? So every node has degree 3, right. So 4 minus, so then it would be 1 plex, 4 minus 3, right. Let's take another example. Let's take 1, 3, 4, 5, 6, this one. Okay. So 1, 3, 6, 4 and 5. Okay. So the S is 5. Okay. And what's the minimum degree? The degree here, the degree is 3. Degree is 1 to 4. This is 1, 2, 3, 4. This is also 4. This is also 4. So node has at least degree 3. So this would be 5 minus 3 plex, meaning 2 plex. Okay. So you can relate this with something called core periphery structure that we have discussed earlier, right. So here we go. So we have the next definition, which is K core. So K core we have already discussed earlier. Okay. So the idea behind K core decomposition is that we discussed in the network measure chapter, in chapter 2 I guess, where we discussed that what we do in this case, we first remove nodes with degree 0, we keep on removing nodes with degree 0, and then those nodes which have been removed, those nodes form the first periphery, right, or core 1. Then you keep on removing nodes with degree 1 until unless you see there is no node with degree 1, then that would form core 1. Then you keep on removing nodes with degree 2 and so on and so forth. So core 0, core 1, core 2, core 3 and so on. You see here all these blue nodes, right, they form core 1. Then these green nodes, they form core 2. These yellow nodes form core 3 and so on and so forth. Okay. So these are the node-centric metrics that we generally use for community detection, but these are kind of old school methods that we used to use earlier days, but these days we basically use more sophisticated techniques. So, in the remaining part of this chapter we will discuss even more sophisticated techniques. Okay. Thank you.